In this video, we'd like to prove that the square root of 5 is an irrational number. So let's start by kind of gathering our thoughts, and so I'll call this the pre-proof work. We're just going to gather some of our thoughts, write down some definitions, and then get ready to write the proof itself. So the first thing that we should do is write down the definition of rational. So we're going to say that we're going to prove that the square root of 5 is an irrational number. But to do that, we need to know what it means to be rational. And in a previous lecture, a very recent previous lecture, we proved that this definition that I'm about to write is equivalent to the one that we gave at the beginning of the course. So it's the following. So a number q is rational if and only if there exist integers m, which can be any integer, and n, which has to be positive, who share no common factors, or I should probably say that share no common factors, and for which q is equal to the ratio here, right? So q is equal to the ratio of m divided by n. All right, the no common factors here is kind of the new part that we added to this definition that we had to prove. We did that in a previous video, so please check that out if you haven't seen it yet. The other thing that we need here is we need a lemma, and this lemma has also been proved in two parts in a couple of previous lecture slides. So the lemma says the following: a number, let's call this number x just for the sake of simplicity, but a number x is a multiple of 5 if and only if x squared is a multiple of 5. Alright, and here I said a number. This is a convention in our book too. When we say number, we mean integer unless otherwise stated, but I'm going to state it clearly here. An integer x is part of the reason that I wanted to change that is because I used x, right? So an integer x is a multiple of 5 if and only if the number or the integer x squared is also a multiple of 5. And we proved this in a couple different lectures. It took 2 lectures to prove this. So proving from left to right in this direction, this is a direct proof. So that goes back to the lecture on direct proofs. And then going the other direction, that was a proof by contraposition. So that was a contraposition proof, but we got both of them, so we can take advantage of both of those. Now, if this number was anything other than 5, we would have to repeat the argument and we'd have to prove it again. But we've already done this for 5, so we are good to go, right? So what we're going to do now is we're going to prove our statement that the square root of 5 is irrational. But remember that irrational means not rational, so this statement is almost begging us to do a proof by contradiction, to assume the opposite, because the only definition of irrational is that the number is not rational. So that's all we would have to work with there, which means, you know, we'd be trying to negate this definition somehow. So this is going to be a proof by contradiction. Let's get onto it. Let's see. Okay, there we go. So we state that we're starting our proof. Our initial assumption in a proof by contradiction is the negation of the original statement, right? So let's suppose that the square root of 5 is indeed rational. All right? Then we can apply our definition, right? So then there exist integers m and n such that m can be any integer, right? N is a positive integer. The main thing here is that n is not 0. That's the assumption there. And m and n have no common factors. So they have nothing in common, no common divisors or factors. And that their ratio equals the square root of 5, right? So that's the key here. And the square root of 5 is equal to the ratio of m divided by n. All right, well, at this point, we just want to use basic mathematics, and we're dealing with a square root of 5, so it would be nice if we could get rid of that square root and just have the integer 5. And so let's do it, right? So squaring both sides, let's see what happens. Squaring both sides, let's see, we've got the square root of 5, quantity squared, equals then the ratio m over n, quantity squared. And then what does that yield? Well, how do you square a fraction? You have to square the top and the bottom. And again, we've assumed that n is not 0. So what we can do is we can square the top and the bottom and multiply the n squared to the other side, all in one fell swoop here. When you square the square root of 5, you get back 5, right? So we get that 5n squared is equal to m squared. All right, well, this then tells us that m squared must be a multiple of 5. It's equal to 5 times an integer, right? So let's write that down. So thus m squared is a multiple of 5. And what does this tell us? Well, this is where we need the lemma. So we go back up to our pre-proof work up here, and our lemma says it's go in both directions, right? But one of the directions says that if x squared is a multiple of 5, then x is a multiple of 5. All right, and that's what we're going to apply here, right? So m squared is a multiple of 5. We can then deduce by the lemma. Right? If you're going to do this, you have to state the lemma, right? If you're going to say by the lemma, you have to state the lemma, and we did state the lemma. So by the lemma, m itself is a multiple of 5. All right. Now, if you're going to prove this for any number other than 5, you have to prove that m squared being a multiple of 5 implies that m is a multiple of 5 as part of this proof, right? But now we know that this is a multiple of 5 by our lemma. And we can now apply the definition of what it means to be a multiple of 5. Well, if m is a multiple of 5, then there exists some other integer. Let's call it k. So there exists an integer k such that what's true? Well, m would be equal to 5 times k, right? M is equal to 5k. All right? Squaring this, what's going to happen? Notice I'm not being too creative with my connective words here. I'm trying to make sure that the logic is not lost here, right? But m squared is equal to 5k quantity squared, which I'm going to write as 5 times 5k squared. And the reason I'm writing it this way is because now we compare. We've got here m squared equals this, but up here m squared equals this. Well, if they both equal m squared, then they have to equal each other, right? So this implies further that, I'll write this on a new line, 5n squared is equal to 5 times 5k squared. Well, why is this important? Again, we know how integers work, right? So we can divide by 5 on both sides, and then we see that n squared, by this argument, n squared must be a multiple of 5. All right? So now we can say whence n squared is a multiple of 5. But we just went through this dance, right? It feels kind of like deja vu, very recent deja vu, because the lemma now implies that n itself must be a multiple of 5 by the same exact reasoning that we use for m, right? So the lemma, once again, the lemma implies then that n is a multiple of 5. And if it feels like we're kind of going in a little dance here, around in circles, we are, right? But look at what we've just shown, right? So let me get out a highlighter here so we can highlight the key things. In our assumption that 5 is rational, right? That was our assumption. Part of that definition of rational is that these m and n have no common factors. So that's part of our definition of rational. And then look what we've shown. Number 1, we have that m is a multiple of 5. Just a consequence of this being a rational number, right? Assumed to be a rational number. And then we have that n is a multiple of 5. All right, so we have assumed in some sense, well, a consequence of our assumption is that m and n have no common factors, but then the mathematics of it the mathematical reality of it, we might say, has led to us showing that m and n do have a common factor, right? And this is a contradiction. So you cannot say that they have no common factors and that they share the common factor of 5. That's a contradiction. All right? And so that's what we're going to write next, right? So we have shown that m and n share a common factor. Happens to be 5. We don't even care what it is, but I'll write it. Shares a common factor of 5, but this is a contradiction, right? And this is the whole key to the proof right here. This is the contradiction. This symbol right here looks kind of like a bunch of roads crossing, some kind of crash happening or something. This symbol right here indicates contradiction. So there we go. We see where the contradiction is. All right, and because we've reached a contradiction, what do we conclude then? Well, we conclude that our original supposition, our original assumption, must be false, right? And so if this is false, then that means that its negation is true. And so now we may conclude that the square root of 5 must be irrational. All right, and we have to write that. So we conclude that this number, square root of 5, is irrational, because that false assumption is what led to this contradiction. So that's it right there. And then we still smile. We have learned, proved what we wanted to prove, learned what we wanted to learn. Now, pay close attention to the structure of this proof, because you will see it again. You probably won't see it with the number 5, but you might see it with a 2 or a 3 or a 7 or some other number there in place of the 5. And the structure of this, you need to change the lemma. Remember, I've said that a few times now. You need to change the lemma if you have a number other than 5. But other than that, especially if you know the lemma, then the structure of the proof will be almost exactly the same. Okay, so make sure you understand this proof and that you can reproduce it without having to read or watch this video.